Good morning, everybody, and thank you for coming to this talk. Today, I'm going to be talking about data science. And data science is really sexy right now. Everyone's talking about data science, right? But yes, I'm going to give you a practical introduction. And the reason I call it practical-ish is because there will be some practical stuff, but to understand the practical stuff, you have to also understand the theory. So, my name is Mark West, and I'm an Englishman. I live and work in Oslo in Norway, and this is actually the third time I've been to GeeCON, I think. So for those of you who don't know who I am, I'm a recovering Java developer and architect. I've been working as a Java developer and architect since around 1999. So I've been doing it a while. And in the middle of last year, I got the chance to build up a team of data scientists at my employer, which is called Bouvet in Oslo. And so that means today I'm coming to you from the perspective of an old kind of Java guy who's gone into data science. So it might be an interesting perspective for some of you. And the last thing is, in my spare time, I'm actually the leader of the Norwegian Java user group, JavaBin. And we arrange a little conference called Java Zone. If you're ever in Oslo in September, you should check out Java Zone. But anyway, enough of that. On with the talk. My talk is split up into 3 sections. I'm going to start by defining what data science actually is and talk about the kind of roles you need to work with data science and some tips for introducing data science in your organization. I'm then going to go on and talk about some basic machine learning algorithms. I'm not going to talk about neural networks today. I'm sorry about that, but I'm going to talk about basic machine learning algorithms, which a lot of people use. And finally, I'm going to go through a practical example to show you machine learning and data science in practice. So, right, what is data science? Well, the first thing I did when I tried to work out what data science was, I did what everybody does. I went to Wikipedia. And Wikipedia tells you that data science is an interdisciplinary field of scientific methods, processes, and systems to extract knowledge or insight from data. That's a lovely quote. But what does it mean? Well, if we delve down into it a little bit, we'll get a better idea of what it actually does mean. And the first thing that is here is interdisciplinary, this buzzword here. What does that mean? Well, I would argue most people in this room are working with some kind of computer science, and they're using computer science to, along with their domain knowledge, to create software. So you have domain knowledge of your customer or your employer, and you create software to solve the business needs. Now, what I would say is I would argue that data science needs an extra facet. It needs an extra skill set, and that is basically maths and statistics. Because, data science and machine learning is a lot about applied statistics. So the data scientist is the kind of in the cool spot in the middle and basically, is a unicorn. People who are just as good as computer science and math and statistics and have excellent domain knowledge, they don't exist. And if they do exist, they've probably been snapped up by Google or Facebook. But for us mere mortals who maybe have a computer science background, what this picture tells us is if we want to work with data science, we need to brush up on the maths and statistics. We go back to our quote, what data science is. The next thing it says, it's scientific. It's a scientific method. And like the scientific method, data science is driven by hypotheses and questions. And your hypothesis can be, can I predict the house prices in my local town based on historical information? Or can I get a car to drive itself? That's the kind of hypothesis you might start with. And when you have that hypothesis, the first thing you need to do is collect your data. And that takes time because you've got to go to all the system owners and the database administrators and say, I want your data. And they're going to say, well, how much do you want? And you're going to say, well, how much do you have? And it's going to go on like that. And they're going to get grumpy and it's going to take time. And once you've got that data, you have to put it into some kind of repository. Maybe you need to aggregate it. I don't know. Gathering data takes time. When you have the data in place, then you can start messing around with it. And here you can start using some basic machine learning techniques to understand how the data hangs together. Are there correlations in your data, or is there data missing? That kind of thing. These first 3 steps are around about 60 to 80% of the data science job. You spend a lot of time kind of understanding the problem. When you have done that, then you can actually start building your machine learning model or your neural network or whatever you want to build. And when you have that in place, then you have to actually interpret the results. Maybe the results aren't what you expected. Maybe the model doesn't give you the results that you expected, and you have to kind of, do a little bit of research to try and find out why you got what you got. And then you have to communicate it to your stakeholders in a way they can understand, right? You have to put, if you start talking about, I don't know, if you start using lots of mathematical jargon, your stakeholders aren't going to understand what you're saying. So you need to put everything into a language they can understand, and then finally you get your result. Now, this process is not sequential, it's actually iterative. The steps are iterative. You can get to step number 3 and realize that you don't have enough data. Or you can get to step number 3 and realize you have to redefine your question because your question doesn't really reflect the data you have. So it's important here to remember all these steps, you can jump back and forwards between them. Now, there's lots of data science processes out there. You have the crisp data mining process, you have Microsoft's team data science process, but they all have these basic steps in common. But there's something missing, a little pop quiz for you all. What is missing from this? Anybody want to guess? Putting it into production. All right, that's what's missing. And that's because putting things into production isn't a data scientist's job. If you're going to work with data science in your job, you're going to need some different roles to be successful. You're going to need the data scientist, you're going to need your rock star who creates your machine learning algorithms, your models and whatnot. But you're going to need the data engineer. You need the person who's going to build your data platforms, who's going to build your pipelines, who's going to take your algorithm or model and put it into prod, monitor it, all that kind of good stuff. And actually, if you want to work with data science, but you don't have a mathematical background, data engineering is probably the best way to get into data science. Not only that, you're going to need somebody to do your visualization. If you have to create some kind of dashboard, you need somebody who can, create a story and create intuitive dashboards for your users. And then finally, you're going to need a process owner, somebody who's going to be a project leader, who's going to manage the stakeholder expectations, because your stakeholders are going to think, oh, we're going to get Skynet in 4 weeks, when in reality it's going to take a bit longer. You need a process owner who can maintain a vision amongst the team, can facilitate. So if you have a grumpy system owner who won't give you data, the process owner can go and give them a bit of a kick up the backside. And you also need somebody who's going to go around your organization and evangelize the data science team. So, data science is a team sport. So back to our quote about what data science is. The next thing is data science. Well, data science is about extracting knowledge. So let's address the elephant in the room. Is data science business intelligence? A lot of people think this. It's like, same shit, different wrapping. One of the signs that you've been in the industry a long time is when you start seeing the new trends coming back again. It's like microservices. It's just SOA. The same with data science. Is data science just BI? Well, I would argue no. That's a big no on that big screen. I would say that data science is an evolution of BI. So data science brings some extra things to the table that BI doesn't have. So traditional BI is very focused on data warehouses, relational databases. So you have structured data. Whereas data science allows you to work more with unstructured data, pictures, audio file, unstructured text, that kind of thing. The tools available in business intelligence are generally data visualization and statistics, but when you work with data science, you get access to machine learning. And machine learning, in turn, gives you access to advanced functionalities. The goals of BI are all about, okay, let's steer the ship. What happened last month? What should we do now? Whereas data science is about, okay, do you want this car to drive itself? So, data science has a lot in common with BI, but it actually is a step onwards from BI. So what we're talking about machine learning. There is so much confusing about machine learning. What is machine learning? What is AI? What is deep learning? There's all these sales terms that are being thrown around. And it's actually not that complicated. AI is the very broad term, right? That's about getting computers to be like humans. It's about creating C3PO and that kind of thing. So AI, by definition, isn't just about technology. Right? It's about psychology, understanding how the human brain works so we can actually implement it using computers. It's about philosophy. What is intelligence? It's also about hardware. To have a true intelligence, it has to be able to move around and interact with its environment. So AI is a very broad term. And that's not what we're working with in the industry today. We're working with machine learning. And machine learning is algorithms. It's applied statistics that allow computers to learn, make predictions, and describe data without you having to program them. And then you have deep learning. Deep learning is nothing new. It's neural networks. I wrote my master's thesis on neural networks in 1993. That's how old I am. So neural networks have been around for a long time, but it's only now that they're being used in industry, right? And the thing with neural networks and data science is everybody wants to play with TensorFlow. I want to do data science. I want to learn TensorFlow. But you need to learn to walk before you can run. And if you go straight into neural networks, the chances that you're going to fail are very, very high because you need to build up some basic data science skills first. So I'm not going to talk much about deep learning today. I'm going to focus more on standard machine learning. So I'm at the end of the first part of my talk now. I just want to sum things up. Data science is about, or data scientists require math and statistics in addition to traditional software development skills. Data science is hypothesis-driven and has a process. Data science projects require a range of competencies and skills, so math and statistics in addition to traditional software development. And data science can be seen as an evolution of BI, but it gives you extra capabilities through machine learning and unstructured data. So that's the first part of the talk out of the way. Now I'm going to talk about machine learning algorithms. I'm going to start looking at a few machine learning algorithms and explain a little bit more about how they can be used. So just to remind ourselves, machine learning is about allowing computers to learn without you programming them. So it's like, well, if you like Spring, you'll like this. Machine learning is like an inversion of control, where the computer or the algorithm writes the rules instead of the human writing the rules. Let me just see if my clicker doesn't want to work. Oh, it just reconnected. There we go. There are three main types of machine learning. And the first one is supervised learning. So supervised learning is like having a child and you show them pictures of an apple and you say, what is this? And after a while, the child starts saying apple. And basically, supervised learning is used for prediction. So building models that can predict based on patterns they find in historical data. Two examples of supervised learning. One is facial recognition. So you teach an algorithm to recognize pictures of you. Or another alternative is predicting house prices. How house prices may rise and fall based on previous house sales data. Then you have unsupervised learning. Unsupervised learning is a bit different because that's not about prediction, it's about finding trends. So it's about describing your data. And a good example of unsupervised learning is if you have customer data, customer sales data, and you feed it in to an unsupervised learning algorithm, that algorithm will try and group your customers together based on their attributes or their activities. And this is like clustering, basically. This can create new customer segments. And then we have reinforcement learning, which is the sexy beast of the whole lot, which everyone's really excited about. It's nothing new, but reinforcement learning is about a model that learns, it takes feedback from its environment and adjusts its strategy all the time. So a good example of reinforcement learning could be a machine learning algorithm that actually buys and sells stocks and shares in the stock market and tries to improve its strategy over time. And again, reinforcement learning is at the bleeding edge. I mean, even though reinforcement learning has been around a long, long time, it's not something that's used a great deal in industry today. Yeah, Google and Facebook, the big guys are using it, but depending on your where you work, you probably aren't going to be working with reinforcement learning in the near future. So I'm going to talk about just supervised and unsupervised learning. And I'm going to talk about regression, which is about predicting continuous values. I'm going to talk about classification, which is predicting a class. And I'm going to also talk about clustering. I'm going to show you some examples of how to do these. But first, when you're building a model, especially a supervised model that's going to do prediction, you have to create something that's relatively generalized. Now imagine you go back to work on Monday and your boss says, oh, I know you're at GeeCON and now I want to get some benefit out of it. I want you to create a machine learning model that if I show it a picture, it can tell me whether there's a sheep in the picture or not. And how would you do that? Well, of course, you would train your model up with lots of pictures of sheep. And the idea is that your model would try and work out what characteristics or attributes that all sheep share. That's what it'd be trying to do, basically. So in the worst case scenario, you'd end up with a model like this, which would all sheep look like that. It hasn't managed to recognize any characteristics of a sheep at all. And it could be your training data isn't good enough, or you didn't run enough training rounds. something like this might be a bit better. This is a more generalized model. Here you have like it's like a child's kind of, depiction of what a sheep looks like. You've got the eyes, the mouth, the two ears, the body, the four legs, and the tail. And this, it captures the generic patterns of a sheep, but it might have an error margin. So if you show it a picture of a sheep without wool, it might fail, right? But that's the thing. When you have a generalized model, it will never be 100%. What you don't want to have is an overfitted model. An overfitted model is like one that's basically memorized the training data. So it hasn't managed to find the general characteristics of all sheep. What it's done is it's memorized the training data pictures it's been shown. So when you try and show an overfitted model new data, it won't work because it's just memorized, right? It's like a child that when they're in an exam, they remember everything as they've learnt it, but they've not actually understood the information they've learnt. So that's the difference between a generalized and overfitted model. And what we really want is generalized. So it's like a sliding scale between underfitted and overfitted. We don't want it to be too generalized. We don't want it to be too specific. But the challenge there is finding the balance. And to do that is going to depend a lot on your specific use case. But anyway, with that out of the way, let's talk about some simple machine learning algorithms. And I'm going to start with I'm going to talk about some simple stuff because I believe that machine learning and data science, you should start with the simple stuff before you go on to TensorFlow. And the main reason for that is that TensorFlow neural networks are often stacks of algorithms. So you have to actually understand how these algorithms work. So I'm going to start with linear regression. Linear regression is simple. It's so simple that most people don't even, see it as machine learning, right? I have some data here. I have some data that tells me house prices based on the size of houses. So it's historical house sales data. And what I want to do is I want to create a model that predicts new house prices based on the size of the house. So I split my data up into a feature and label. The feature is what's going to be the input, and the label is my historical output. And luckily, because I'm only using 2 dimensions, I can easily plot my data. So I take my data and I apply linear regression to it. And this is the model. That's what the model looks like. That blue line is my linear regression model. It can also be described as a trend line. And what it's trying to do is draw a line that's as close as possible to all of the data points that it finds. And what I can do with that line, I can use it to predict new house prices. So if a house goes in the market for, let me see, with 5,000 square meters, I can expect to get 1.5 million for it, according to the model. Now, of course, this model isn't that good. It's a bit oversimplified, so we get a lot of deviations. Deviations tell us that, this model isn't as good as we think it is because we haven't really paid attention to all of the features. We've only taken the size of the house. We haven't thought about where the house is. We haven't thought about, does it have parking? Does it have 3 bedrooms? All that kind of stuff, right? So this model is oversimplified, which this deviation kind of indicates. Now, how we draw that line, there's different algorithms for drawing that line, but one of them is ordinary least squares. It's the easiest one to understand. So if you imagine that this is a linear regression model where the green line is our actual model, we measure the points, the distance from each data point to the model. We square them, add them together, and that's the sum of squared error. And when we do linear regression, we're trying to reduce the sum of squared error as much as possible. So that's how the line is fitted. And the danger here is outliers can actually affect our model. So an outlier is an anomaly or an error in our data, which kind of maybe drags our trend line away from where it should be. So if this C variable here is an outlier, then it's actually dragging our trend line upwards. So you have to watch out for outliers when you're working with data science, and you have to work out whether you want to just remove them or whether you want to normalize them or do something else with them. So that's linear regression. Linear regression is so simple. It's easy to understand, easy to explain, it's transparent, but it has some weaknesses. Outliers will skew the trend line. It doesn't work with non-linear relationships, obviously. But there are non-linear alternatives that can give you regression models if you need them. The next algorithm I'm going to talk about is decision trees. And decision trees is obvious to all of us here because we're developers. That's what we do. We build flows, right? So decision trees are pretty simple. And basically what decision trees do is they calculate the best split on your data. Now, a question for you guys. Do you get bothered by British recruiters? Oh, God, it's not just Norway. These bastards are everywhere. All right, I live in Norway. I get played by these British recruiters. I'm British, and I'm embarrassed to be British. These recruiters are nightmares. They phone you up weekends, evenings, holidays. I've got a great job for you. Do you know any J2EE? I hate them. But imagine that these British recruiters came to me and said, Mark, we want you to build a decision tree that can tell us who should get a pay rise based on historical data. So I take some information from previous years, and this information I split into features and labels. So have they made any placements? Have they received any complaints? Have they lived in Norway? This is, because like most of the British recruiters have never been to Norway when they ring me up. They don't know the language or the culture or anything. It's really frustrating. And whether they got a pay rise. So if I take this data here and feed it into a decision tree algorithm, the decision tree is going to try and find the feature that best splits my classes into either got a pay rise or didn't get a pay rise. And it's pretty obvious that the one that does the best split is placements. All of those who made a placement got a pay rise. None of those who did not make a placement got a pay rise. But if we look at the other features, we see complaints doesn't give us a good split because we have people who got pay rises and didn't get pay rises on both sides. And the same with lived in Norway. So it's obvious that the best split is placements, right? And that's fine when you've just got, when you get that kind of situation where just one feature splits your data is brilliant. But if it's not that simple, and it rarely is, then you're going to have to do some kind of recursive partitioning. And this does exactly the same thing. This is a different data set. Should I play golf depending on the outlook, the temperature, the humidity, and the wind? Right, okay. So my algorithm, what it would do first, it would find the feature that best splits my data. And in this case, it's outlook. Because all of those that are overcast, all of those data points with overcast set to yes, say that I can play golf. So the next thing what will happen is the algorithm will go down and it will look at the sunny line. So every data point that is sunny, what is the feature that next best splits the data? Humidity. Great. And the same on the rain side, wind. So we see that temperature is completely ignored in my resulting decision tree. But that's how decision trees work. It's very, very simple. But where do you stop building them? In this case, it's obvious because like when I got to the end, all of the leaf points belong to the same class. So that was a natural stop. But if the decision tree was more complicated, you have to find another metric for stopping the building. Make sure the decision tree doesn't go too deep. And one example is using the maximum tree depth. And I'm going to show you that when I do the practical side of my talk. Another thing with decision trees, and this is the same with all machine learning, if you get bad data, you could end up with like modelers that don't really give you the behavior you want. So if my British recruiter data has said that everybody who got a complaint got a pay rise, that would be the decision tree models. They would carry on getting pay rises for getting complaints. I actually think that this is how British recruiters operate. The more complaints they get, the more money they get. You'd think so anyway, bastards. Anyway, decision trees. They're white boxes. It means that you can see what's going on. They're flexible. They're robust to outliers. And they handle nonlinear boundaries, but they are susceptible to overfitting because depending what information you put into them and where you split the data, you can get different results. Decision trees also, if you're going to work with decision trees and try them out, you should definitely look into random forests because decision tree is just one tree, but with random forests, your algorithm will generate lots of trees and then aggregate them together so you get like the wisdom of the crowd. So just a little tip for you if you want to use decision trees. The final algorithm I'm going to talk about is k-means clustering. And k-means clustering is basically, it's about grouping your data. This is unsupervised learning. It's about grouping your data. Now, I've plotted 150 data points here. And anybody want to guess how many clusters there are? 3. It's obvious, right? Because you're using your brain. You're able to look at this and you can kind of work out how things group together. Our brains are wired that way. But a machine learning algorithm can't do that. It has to find some kind of mathematical formula for actually finding 3 groups. So k-means clustering is about finding the amount of clusters, and k means the amount of clusters the algorithm will try and find. That's what you're going to specify. And k needs to be large enough to extract meaningful patterns, but small enough that clusters remain distinct. So with this data here, if you tried applying 10 clusters to it, it would be meaningless. And if you tried to apply one cluster, that would also be meaningless. So we need to work out how we can calculate k. And one way of calculating, which I like because it's visual, is again using the sum of squared error. So the sum of squared error, to remind you, it's the distance that each data point is from the center of the cluster. And then you square those and add them together. So it's just like the linear regression example I showed you earlier on. So how sum of squared error works with clusters is that the more clusters you have, the smaller the sum of squared error is. So I'll give you an example. If you look at this data here, if I apply 2 clusters to it, the distance from each blue point to the red center will be squared and added together. Now, if I do the same with 4 clusters, you can see the distances are shorter. So the sum of squared error will actually be smaller. And I've actually plotted my data here. So the 150 data points I showed you at the beginning, I've created what we call a scree plot. And this is basically showing us the number of squared errors depending on how many clusters I applied to my data. And we can see here, like I said, the more clusters I have, the lower the sum of squared error is. And the trick here for working out what k should be, how many clusters should I try and find, is basically it's the elbow of the plot, which is there. So, yes, 3. So how does this work in practice? And what happens is I start my algorithm with k set to 3. And the first thing it does is it sets 3 data points or 3 centers for my clusters randomly in my data set. And then it applies, or it basically calculates cluster membership based on a nearest centroid. So all those guys that are closest to the, that one at the top, they all become yellow and so on and so forth. But now the centroids are no longer at the center of their cluster, so we have to move them. But then we have to recalculate our membership again. And then we have to move them and so on and so forth. And after 6 iterations, the clusters and the centroids stabilize and the algorithm stops. So that's how k-means clustering works. What's really good about this is it's really, really quick. Because it's just measuring Euclidean distance. It's not doing anything that complicated. So it's definitely one of the things, along with decision trees and linear regression, that data scientists use first when they get hold of new data. So k-means clustering is fast, but it's really biased towards round or spherical clusters. If you have a cluster that's elliptical, k-means clustering might not be so good. And also, k-means clustering assumes that each data point can only belong to one cluster. Okay, so machine learning algorithms, some key takeaways. 3 types of algorithm. There's supervised, unsupervised, and reinforcement. And subsets of supervised are regression and classification. And the subset of unsupervised is, now I've got clustering. Sorry, I've got a little bit of what we call in Norway iron carpet, which means when you get forgetful. Machine learning is more than just neural networks, because I showed you some algorithms. These were simple algorithms. There's a lot more complicated algorithms out there. But what I really want to get across is you don't need to start with TensorFlow when you're getting started with machine learning. A successful machine learning model needs to find the balance of generalization between underfitting and overfitting. And machine learning algorithms are just tools because they're already implemented. All you're going to be doing is feeding your data into them and twisting the knobs of the machine learning algorithms. So the good results will come from understanding your data and understanding your algorithm, how it works. And that's where the maths and statistics comes in. So we're going to go over to our practical example now. And we're going to go for Hello World. Hello World in the data science, if anyone here has done any data science, you're probably rolling your eyes now. It's Titanic. And the reason why I'm going to talk about Titanic is everyone's seen Titanic. And if you haven't, you've read about Titanic, right? So basically, I'm going to build a classification model that's going to predict survivability. I have a hypothesis that I can predict survivability based on age, gender, and ticket class. Age and gender, because women and children first. There's that paper, that's a paper up there that says like women and children first, right? And ticket class, because in Titanic, Leonardo DiCaprio is in 3rd class and dies. Right, this is the data I'm working with. And it's a standard Titanic data set, which you can download online. This is a very standard thing. I'm not going to go through all the different columns here, but I'm going to say that I'm interested in survival. That's my label. That's what I want to predict. And I want to predict it based on P class, sex, and age. And just remember that ticket class, 1 is first class, the best, and 3rd is worst class. So 1 is Kate Winslet, 3 Leo. So tools that I'm going to use, scikit-learn, which is a Python library for machine learning, and it contains lots of machine learning implementations. So it's really, really cool. It also wraps up some other Python libraries such as NumPy, which is good for maths, Pandas, which is good for data sets, and Matplotlib, which is good for visualization. I'm using the Jupyter Notebook for my code, and Jupyter Notebooks are great because you can write code, add comments, create visualizations, and you've got it all in one sheet, which you can show to your fellow data scientists. But Jupyter Notebooks are nothing you can put into production, really. They're just more for the exploratory stage of data science. And the last thing I'm going to mention is Anaconda. Now, the reason I mention Anaconda is it's actually a distribution that contains scikit-learn, Jupyter Notebooks, and lots of other stuff. So if you want to play around with data science tools, just download the Anaconda distribution, and you'll get started a lot quicker. Right, so I'm going to go over to my Jupyter Notebook now. Normally, this is a problem, this Jupyter Notebook, because I have to zoom in and out of it. But with this massive screen, I think I'll be all right. Now, this is the Jupyter Notebook, just zooming through it with all what I'm going to be showing you. Now, luckily, you can actually add a plugin which allows you to go into presentation mode. Yes. So the first thing I do is I take my data set and I import it as a CSV file. And it's called train CSV. Now, if I zoom into my data a little bit, I don't know if you can make out. Can you make that out yet, or do I need to zoom in more? Yeah, it's good. So we can see we've got all our data. And what's interesting here, well, there's a few things that are interesting. One is that, the name actually includes the honorific. Now, the honorific is Mr., Mrs., that kind of thing. But what's also interesting is that a lot of the age values are missing. And that's a problem. We're going to create a predictive model based on age, and we're missing age in our training data. So the next thing I do is I just do a simple statistical analysis. I do something called a describe. Now I'm going to zoom in into that as well. Now, what I'm doing here is I'm asking basically pandas to create a very simple statistic analysis of all the numerical values in my data set. And what I find out here is that I have 891 rows. But I also find out that I've only got 714 ages. I'm missing 177 ages. So my data's not very good. I can also work out from this that 38% of my data set actually survived the Titanic. And I look at that, I can see that by looking at the mean survival value. Because survival is set to 1 if they survived. And the mean value is 38. So 38% of my data set survived. So just by doing a simple describe, you can actually start to understand your data. And we know Titanic, but if you don't know the domain that well, this kind of thing can really give you a lot of insight. So I'm going to do some feature engineering. Now, feature engineering is part of the data science job. This is part of the data exploration. And it's basically taking the data you have and creating new features out of it, new variables out of it. So we have a problem. We're missing age values. And I could just delete all the rows missing age values, but I'd lose a quarter of my training data. So I'm going to guess those missing age values by basically calculating the median ages based on the honorifics. So the median age for all the Misters, the median age for all the Misses, and that kind of thing. So I extract the honorifics and add them to my data set. And if I zoom in here, you'll see that I've got a new column now, which is called honorific. And then I'm going to look at how many honorifics I have. So I'll just list them all here. So we have lots of different honorifics here. We can see that a lot of the people in my data set are Misters. But we can also see there's some very strange ones in here as well. We have John Keir. I had to Google that one. I think it's Dutch for sir. Madame, that's obviously French for Mrs. No, for Miss, sorry. No, Mrs., yes, sorry. Mademoiselle, that's French for Miss. The Countess. You know, there's some weird ones in there. I'm going to normalize these just to make life a little bit simpler. So what I'm going to do is I'm going to create a simple map, which I'll show you now. So basically, yeah, you can see the whole map. Captain, Colonel, Doctor, Major, Rev. I'm just going to call them all serviceman Because in my mind, in kind of like the time of Titanic, all of these people were probably men, and there are probably around 40, 50. So it's just a stereotype I'm applying, but just to make things a bit easier. I'm also going to translate John Keir and Don to Sir, and I'm going to translate the French names also to English names. So I end up with a lot less honorifics. So if we just go to the next page here, now what we see is a box plot. And the box plot shows me my honorifics that I have: lady, master, miss, Mr., Mrs., serviceman, and sir. And it shows the distribution of the age values for each of these groups. And the green line is the median age, which I'm going to use. So we have the lady is just over 40, master is around about 7, miss is about 21, Mr. 30, Mrs. 35, serviceman 50, and finally sir is around about 40. So I'm happy with that. So the next thing I'll do is just some simple Python, and this is just to basically 2 loops, one to create the median age and one to populate the missing age value. So that's not really that interesting, so I'll just hop over that. The next thing I'm going to do with feature engineering is fix the categorical variable, which is now set to male or female. I'm going to just change that to 0 or 1. So if we look at the data set now, we can see that sex is set to 0 for male and 1 for female. And now I can do some visualizations to see if the data reflects my hypothesis that, survivability could be predicted by age, gender, and class. So the first thing I'm going to do is I'm going to plot all of the values. Just zoom into this a little bit more so you can see it. So I'm plotting all the values by class. So the blue values are those who died, and the orange or the brown ones are those who survived. So you can see if you travelled in first class, you had a better chance of surviving. So if you were Kate Winslet, the chances were on your side. Leonardo DiCaprio, on the other hand, he was in the shit. Basically, you can see that your survival chances were a lot less if you were travelling in third class. Okay, what about gender? And this is just as bad. Sorry, chaps, but if you're on the Titanic, yeah. Basically, you can see here that many more of those who are male died than survived. And on the female side, you had a better chance of surviving than dying. What about age? Age is an interesting one because age is a continuous variable. So I have to do something with that. I had to create a new feature, which basically tells me if someone is adult or child. So basically, everybody under 15, I count as a child. Everybody over 15 and over, I count as an adult. And then we see a slightly different distribution. So we see, more adults died than survived, and more children survived than died. But the difference between the children values is actually quite small. And I got to thinking about this, and I realized that age is very tightly tied to things like class. Because if you were traveling with your parents and you were say 5, and your parents were in third class and died, then unfortunately the chance of you dying were pretty high as well. So age on its own isn't a good indicator necessarily, but combined with the other variables, it is. So now, the moment of truth. We start getting rid of all of the crap in our data set we don't need to have anymore. So we're just basically keeping the label survived, P-class, sex, and age. We're getting rid of everything else, just so we don't end up by polluting our model. We start building our decision tree. So the first thing we do is I split our data into features and labels. So we have our 3 features in the feature set and labels in our label set. And we split our data into training and testing set. Now, this is a very important thing to do. When you're working with machine learning, you should never test your model with the same data you use to train it, because all you're doing is checking if it remembers. You're not checking to see if it's managed to create a generalized model. So it's always important to separate. If you have some data, put aside 25% for testing. And now I'm going to do the machine learning bit. There you go. That was it. Because machine learning algorithms are already written. You just put your data in there. And this is very important to kind of pull across that, the machine learning is all about messing around with your data and then tuning the actual algorithm. It's not about writing the algorithm yourself in this day and age. So I'm training the decision tree with my features and my labels. And I'm not setting any of the parameters. I'm not twiddling with any of the knobs on the machine learning algorithm. I'm just using the defaults. So next thing I do is I'm going to actually test my model using my testing set and calculate the accuracy. So already I'm on 75%. It's not bad. Pretty happy with that. I didn't do much, you know? But like what we're not seeing here is all the effort I would have had to put into understanding the domain if I hadn't known it already. So I'm getting 75%. That's good. Let's have a look at the model I've created. Oh, no, sorry. First we do that, we're going to look at the confusion matrix. The confusion matrix is very useful because what it does, it tells us, it gives us an idea of how I did on the prediction side. So we can see here that, like, I correctly predicted that 114 died, and I correctly predicted that 53 survived. So it's not bad, but I made errors with 56 of my test data points. But let's have a look at the tree now, decision tree. Ooh, it doesn't even fit onto the screen, it's that big. That's overfitting, because I let the tree just build and build and build itself. And, you know, I have three features. And yeah, this is no good. This is no good. We need to do something about this. I think I can improve my model by removing the overfitting or reducing the overfitting. And the best way to do that is to actually say to the tree, I don't want you to be any deeper than a certain level. In this case, I'm just going to guess and use a rule of thumb and say, let's set the number of features to 3. Okay, let's try that. So I build a new model. So all I've done here is I've just set the hyperparameter max depth to 3. And I test and score it, and I get already 5% better. I'm on 80% now. Just by, you know, tuning the tree. I actually improved my model by 5%. So I'm pretty pleased with that. Can you all see that 79%? I can't, yeah. And let's have a look at the confusion matrix. Now I can see that before I had like something like 53 or something errors. Now I actually have 45 errors. So, you know, all I've done is I've just improved my model by 8 data points. But still, it's improved it just by doing a little tweak. Now, if you go to Kaggle, which is what data scientists use for messing around with data and, you know, posting what they've done and comparing notes, there are lots of people on there that have got very, very good scores, like up to 100%. But if you look at like how they've worked with the data, you have a very, very long Jupyter notebook where they've done lots and lots of stuff. So all I'm doing here is just giving you a very quick example of how you can use feature engineering and machine learning. If we actually look at our decision tree, our new decision tree is, you know, a lot more tidier, easier to visualize, possibly easier to show to your stakeholders. So that's the demo. I just want to say a couple of quick words before I let you go for lunch. One of my goals was to actually be finished before 12, so you can run to lunch. I know how it is when you're hungry. Some key takeaways. Scikit-learn and Jupyter Notebooks are a really easy way to get started. You don't have to pay any money. It's free, right? You don't have to pay Google money or Amazon money. They're going to try and lure you in. But to learn the tools of the trade, just use free stuff. Feature engineering is vital. Actually manipulating your data is actually, you know, one of the biggest things you'll be doing as a data scientist. And domain knowledge, understanding the domain, if you don't know that, then you're going to struggle. Split your data into test and training sets. Do not test your model with the same data you used to train it. And don't forget that tweaking high parameters of your model can give you really good results, but you need to understand how the model works under the cover. Now, my slides, I'm going to be putting them out in around about, well, in the next hour. So if you go to Twitter and look #GeeCON in the next hour, you'll find a tweet from me where I've put a link to all my slides and the code, so you can go and have a look at it in your own time. But other than that, I would just like to say thank you very much for coming. Thanks for listening. And if anybody has any questions, feel free to ask. Thank you. Any questions? It's lunch, right?